Right, so let's continue with our AC steady state power, and this topic will be on apparent power and power factor. And we're going to start off with the formula that we did in the last session, which is the average power, P equal to VRMS IRMS cos theta V minus theta I. Okay, if so from this formula we will you'll see that there is this term here, VRMS times IRMS, the first term, okay, which is like the formula that we have known that P is equal to V times I. Okay, so therefore in AC, however, this VRMS V times I, okay, we call it the apparent power S. So S stands for apparent power, okay, and the formula is equal to VRMS times IRMS, okay, and it's the product of the RMS value of the voltage and current, and the unit is var, okay, volt ampere, okay. So it's not like DC anymore, that when you have V times I, right, the unit is watt. So it's very important that you remember the unit of each parameters. The average power, the unit is watt. The apparent power, the unit is VA. So from now on, you will have to be able to remember that if you see the unit VA, okay, this number referred to as a apparent power, okay. So it's called the apparent power because it seems apparently that the power should be voltage times current, okay, and the unit VA is to distinguish from the average power, or the real power. The second term here, cos theta V minus theta I, is called the power factor, PF. So PF is a power factor, okay, and it's equal to cos theta V minus theta I, okay. Another formula for power factor is equal to, of course, from the average power from this formula, okay, so PF is equal to the average power over the apparent power. So this is the formula for the power factor. The angle theta V minus theta I, okay, is called the power factor angle. Power factor angle. And it's very interesting that that if you look at a formula for the load is equal to the impedance, right? If your load is the impedance, the formula for impedance is phasor V over phasor I. Phasor V over phasor I. And if your V is VRMS, phasor VRMS over IRMS, or equal to VRMS angle theta V over IRMS theta I. So you get VRMS over IRMS, and the angle is theta V minus theta I, which is nothing, is the same as the power factor angle, okay. So therefore it's very interesting to observe that the power factor is the cosine of the phase difference between the voltage and current, okay, of your load impedance, okay, and it's also the angle of your load impedance, okay. So that means that this angle, okay, the power factor angle, can tell us what kind of the load we have. So for example, for inductive load, for an inductive load, okay, well, we know that for the inductive, the current lags behind voltage, Okay, so that means that your theta I, the phase angle for your current, would be less than the phase angle of your voltage. Okay, that means your angle, your theta V minus theta I, right? Your theta V minus theta I would be positive because theta V is greater than theta I, would be positive. So in this case, if your so-called power factor angle turn out to be positive, we can conclude that we can write, when you calculate your PF, you have to add one word such that indicating that this load is an inductive load, which is the word lagging. So we have PF lagging for inductive load. For a capacitive load, right? Well, current leads voltage. So that means your theta I is greater than theta V, and that would lead to a negative power factor angle. And so in this case, for the capacitive load, we would write our PF as PF leading. So if you have a load that is a PF lagging, so you know that, oh, it's inductive load. PF leading, it means it's capacitive load. Okay, so let's look at an example. Okay, let's say that you have a series connected load. So you have a somehow, this big load right here, right, ZL, and inside here it's a series connected, something connected in series, and it draws a current I of t when you have a voltage supply V of t across it. Okay, so and given that V of t then is equal to 120 cos of 100 pi t minus 20 degrees volt, and the current I of t is equal to 4 cos of 100 pi t plus 10 degrees amps. Okay, the question is, find the apparent power and PF of the load, and determine the element of the load. Okay, so let's start. To do this, it's all formulas. You remember formula. Apparent power, right? Apparent power S is equal to VRMS times IRMS. Okay, so which is then equal to, well, it's still given in the problem, give you Vmax and Imax. Okay, because it's in front of your cosine term, waveform. So it's 120 over root 2 multiplied by 4 over root 2 equal to 240 var. Okay. Next one, power factor of the load. So the formula is PF equal to cos theta V minus theta I. So equal to cos theta V is minus 20 minus theta I is plus 10. So equal to cos minus 30 degrees. And the answer is 0.866. And if you realize that cos minus 30 right? And cos positive 30 give you the same answer. Okay. So therefore, when you get your PF values, you have to indicate whether this is a capacitive load or an inductive load. And you know that by, of course, this angle inside, your cos. It's negative, right? So it's negative, right? So it means that it's leading. It's a capacitive load, leading. So you write down the word leading behind it. Okay. So that's the two problems, the two answers you have to find. Next one, determine the elements of the load. So you have to know the value of the load. So your ZL is equal to phasor V over phasor I. Your phasor V is 120 angle minus 20 degrees. Phasor I is 10 degrees. So equal to 30 angles minus 20 minus 10. So equal to 30 angle minus 30 degrees ohms. This is in polar form. In polar form, it still doesn't give you any idea on what type of elements that's connected in series. To do that, you have to convert this back into a rectangular form. Okay, so therefore, using your calculator, you find out that your ZL converted from 30 angle minus 30 degrees turned out to be 25.98 minus J15 ohms. Okay. So now you know that, my ZL consists of this part, the real part, and the imaginary part. If you go back to your impedance, you recall your impedance concept. The first part, the real part, is your resistive load. So it's your R resistors. And this minus J, and this minus J15 is your reactance. So your reactance. So it's represent either your inductor or capacitor. So at least you know one thing, okay, it's an R, right, equal to 25.98. And it's connected to something, but you say it's capacitive load, it's leading capacitive load, right? So that means it's in series with a capacitor with the value of minus J15 ohms. Okay, it's minus J, so you can think of XC. Okay, but then if I want to say, I want the element values, you have to find the capacitor, the capacitance values. Then you have to recall again what the value for the impedance of the capacitor is, right? Right, ZC is equal to minus J over omega C. So it's equal to minus 15J in this case, right? Your omega is equal to, you look at your problems, 100 pi. Your omega is equal to 100 pi, right? So therefore, your C, this all cancel out, right? So therefore, 1 over 100 pi C is equal to 15. So therefore, your C is equal to 1 over 15 times 100 pi equal to 212.2 microfarad. So therefore, your elements that's connected is 25.98 ohms, your R, and the capacitance is 212.2 microfarad. And that's the answer. That's how you do things. Okay. Okay. So that's it for apparent power and a little bit of power factor concept. Thank you.